Hello and welcome everyone. So in the previous session we have started EDA, that is explore data analysis. Then we also said that in these series of sessions we'll also look at data preparation and pre-processing, and maybe we'll also, not maybe, just for sure, we'll also look at feature engineering. So how to engineer the feature engineering. Okay, I have given some introduction about all these topics, what these things are, and we'll continue from where we left the last session. So just an heads up over here. So one thing that we'll see about them is we'll do these things on different data sets, and after that we'll take it one by one on maybe a particular problem, and then we have to do that because you now know the machine learning pipeline, how machine learning pipeline works. You have data and different steps happen until you get a model, then you test the model and all this stuff. So we'll take different data sets. It won't be just one, and I won't just take problem per se. I'll just take it on data set and perform this. And once we go at the stage where we have to solve some problem, that you'll have to figure out on your own. Okay, what type of processing should I use? What feature engine should I use? And what type of EDA should I use? Okay, I'll just give you ideas. As I said in the previous session, sometimes this EDA, doing an EDA becomes more of an art, because the more you do it, the better ideas you get. Okay, and as I already told you that this is open ended. You can ask a lot of questions to the data till it gives you the answers and you understand the data well. Okay, and we are at this part EDA, and I introduced some things about this. Then we saw what are the different steps that are involved in data processing and preparation. So in that, the first step was, if you remember, handling missing values. Okay, so where do we get these missing values from? Okay, so now if you see the data, as I told you how to collect data, you know about data collection, how to collect data. It can be from the primary sources, it can be from the secondary sources. But sometimes what happens is, while you're collecting data, some features you won't have the values for. Sometimes for some data points, some features won't have values. Either inherently they were not measured, or they were not taken when the observations were made, or sometimes they are misplaced or something and people just don't fill them. Okay, that's what we get missing values from. Okay, we get missing values from either data not having them. Okay, while collection the data, they are not taken. Okay, or maybe somehow some tampering happened with that and that value got removed, or something happened to the data. Okay, these are two reasons. The first reason is data collection at this time. Some people may not even pick the data, or sometimes it happens that there is no way to collect that feature for that data point. Okay, that happens during this data collection time. Okay, one more thing is that it might get tampered. Something happened to the data, or maybe when we were transferring data, you had something and something tampering happened, and it became, the value became nonsensical. You can't make sense out of it, and then you will also consider that as missing value because you don't have value for that. Okay, that's how you should look at these things, because we'll be solving real world problems. You should think all of these things that I'm telling you. It's not that I'll just directly come to, okay, handle missing values. The first thing is you should find the source of missing value. Maybe if you know about the source of missingness, what is the source that made this value missing, maybe you can correct it in a better way. You should ask your question that, okay, it has a missing value. Let me ask this question: why is the values missing? Did it happen because of data collection? Okay, and if it happened because of that, so now the point is, let's suppose your model is continuously training. Yeah, you are again collecting data and then again training the model. So it is better to find the source. Oh, this is the source of missing value. So now if you can somehow figure out that, and the next time you get the data, you probably will have figured that out. Why was this missing value there? Okay, that's the first step you should do, because you will be working in real world and these things do happen. You should know the source and where it comes from. That's why I told you these are the main steps, and many other reasons can be there, which probably I might have not encountered in my duration of doing data science or machine learning. Maybe you will encounter a different problem and then you will have to find. But this is common. Okay, that you have to find the source of. That's why the missing values are coming from. Okay, again, to reiterate, I'm not teaching you all the stuff. Okay, you'll memorize this. No, I'm teaching you how to think. So this is a thinking process. So if you see this, so if now I just teach you, okay, this is how to handle missing values, but you don't know the rationale behind where a missing value is coming from. Okay, and why are these important to sort of handle, and why should I care about these things? So when you go to the data, when you go to the real world problem, and this problem will be there. Sometimes people say, okay, how many missing values are there, and then they start filling out and know all these techniques. But the major portion they miss is, maybe the data will be collected again, and maybe same missing values will come up. So shouldn't we just figure out the source of the missing value? Okay, what is making these values missing? If it is a data collection method, maybe you can tell the people who are annotating data or doing data collection, oh, there are missing values and frequent missing values at this, and this is tampering with my distribution or something. So can you do this, so that I don't have missing values in the next iteration? Similarly, if the data is, if tampering is happening, maybe you can do something else. Okay, while transferring the data, okay, and you are using some other techniques. So if you find the source, it will benefit you a lot. Okay, I just gave you some few instances how can it benefit, but while doing any real world problem, these are questions you used to ask. Okay, I have missing values. The first question is, where is this missing value coming from? Now, why should we handle the missing values? Okay, why to handle the missing values? Because sometimes we feel, because machine learning model, they learn the data that you show and they don't have ability to figure out the missing values on their own. But if you see humans, okay, if you see humans, if there is a missing information, somehow our nervous system is trained that it completes the information. Sometimes you may just see tail of a dog. Okay, from that tail you can guess, oh, there's a dog coming, and you can do a lot of computations. If you see just, let's suppose, some shadow of something, your brain does a hell lot of computation, maybe 100,000 millions of computations to perform, okay, what can I do? Because the brain has to take a decision. If there is a danger, or what decision should I take? So for that, it has performed a lot of computation. That's why if we are given incomplete information, so we somehow can fill that incomplete information, and then we can take a decision based on that. But machine learning is algorithms, the pretty simpler ones, they don't have this ability. If you just show them a tail of a dog and tell them, okay, whose tail is it? Very difficult for them, because usually they are not trained for that specific task where they just see the tail. That's why if you see human tail, it's way above. If you just see a part, if you just see even a shadow, you can figure out from the shadow what it is. Okay, but you have to train a machine learning model for the shadows separately, because you have to have an objective while training the machine learning model. But humans learn without these objectives. Okay, and that's a bigger difference. So now what I'm saying is, first you know the cause of missing value. Oh, these are missing values, and then why should I care about the missing values? And does it make sense to care about these missing values? So what the one thing that is there, I said, if you have missing value for certain points, machine learning algorithms cannot learn from that, because they have to learn. Let's suppose, if you, for a kid, consider a kid as a machine. So if you only show that kid a tail of tails of the dogs, and ask it later, okay, can you identify a dog? He won't be, because probably he has not seen enough data. But humans, they see enough data, and after that, maybe if you just show a part of the data, they'll be able to recognize the object. And even sentences also. Let's suppose if I'm speaking right now, and in between my voice broke, and what happens is, you still heard some pieces of the information, and your brain can reconstruct the other part of the information. If I just said something, some packets got dropped, and your brain is such that, because it has seen so much of this data, it can sort of, what I can call, interpolate or complete these things, so that it makes sense out of it, because our brain is some sort of sensing machine. There's a question, I'll take that. The question was, does it lead to the, let's suppose if we are making a prediction or something. Okay, it's not only the machine learning is not a prediction, it can do a lot more tasks than that. And the question was, does the missing value make the model learn the wrong thing and make a wrong prediction? So the answer is, not all the times, and maybe it may learn the wrong things. But here, what we are, if you see the machine learning models, they want to learn distribution of the data. Okay, what distribution is the data coming from? Now, if you have a lot of missing values, that means your data, the representation is not good at all. The representation that you are giving, the distribution that you are giving to the model is not good. Maybe it'll learn some stuff, but not the actual distribution. And the prediction, making a wrong prediction can be a byproduct. And sometimes it may not even make wrong prediction. The model may give good values, but maybe the distribution of the data, that was skewed somehow. Okay, that's why you should have these points in your mind while doing this. So missing values do not lead always to the wrong prediction. But what happens is, because if the landscape is, let's suppose, in such a way that distribution somehow got skewed because of these missing values, now it learned the wrong distribution in itself. So it is better to have the data in the complete form, the form in which you will give it a kid. As I give an example, if a small kid just saw the tails of dogs, just saw these tails, okay, from the child onwards, and you ask the child, okay, can you identify the dog? Because the child has not seen the dog at all. So probably he or she won't be able to, because the missing value gave it incomplete information, and incomplete information led to the learning of wrong distribution, probably, and the distribution that it was not supposed to work. So I'll add the point here. The task of the machine learning model is to generalize, not to just memorize. Okay. Okay, what's the meaning of memorization? If you see something, you memorize, you spit it out. That's memorization. So generalization is, you find some patterns over there. You find some patterns, and then you use the analytical tools, whatever you have, and then come up with an answer or something like that. So memorization is if I ask you a question and you just memorize the answer to it. That's memorization. But generalization is if you know that stuff, and if I ask some twisted or tweaked question based on that thing and it somehow resembles it. But now what you have to do is you have what information you have to somehow piece that information together and give me the answer. You have to generalize it. So similarly, if I just show human faces to a machine, I'll show, let's suppose, probably some hundred and thousands of faces and ask it for a face which is not in the training data. Okay, that is the task of machine learning. Generalization. And generalization in itself we can discuss over it. It is a mathematical notion also. What's the meaning of generalization? We'll see that in the mathematics portion. But it should not memorize. Okay, this is not what is expected from machine learning model. And now that's why we have to handle about missing values. So this is why. So why part of missing value? Why should we care about handling missing values? Because we don't want our model to learn the incomplete distribution or maybe the wrong distribution. Yes, go ahead. The question asked was if, let's suppose, in a machine learning task you use the text. So what is the new text that you can give it? Because the text is again always made up of the same words and same thing. So what does it learn again? So the answer to that is the thing is if the ordering matters. In what order do you put these words, that matters. So as I already said that if, let's suppose, I have certain information and you have certain information. Now in order to convey that to me, the first thing is that you have to select a certain order. If you select a certain order, then only can you convey that information. As you know that humans have that capability where they put these things in certain order. Okay, they put in a particular order. But other person, they also make a lot of assumptions. The assumption is that other person probably might also know that. They know the same thing. So just again taking one more derivation here. So if you see why are these machines fast, because we can standardize information. Whatever runs on one machine can make other machine work on that also, because somehow they have the same representation data. Now representation, we came to that. We know that they represent information in binary, this and that, and they do it again in the humans. Can we do something? Can we just inject the information? No. Why? Because the representation that you people have in the brain and that I have in the brain, it's entirely different. The representation space that you guys have is very different from the representation space that I have. Okay, and what's the best way to now communicate with people? Now you have to, whatever embedding or whatever representation I have in my brain, I have to take it to your brain. How to do that now? I can't have a device on my brain which will measure electrical pulses, because probably those pulses won't work for you. My data will be corrupted for your brain. If you just take out the data that I have right now and just insert it in your brain, very difficult. Why? Because that will be corrupt information for you. Now, what we have to do, the least thing that we can do is I communicate and I have the similar words. If you see, this is me, these are you, okay, and I have some information. I have to transfer this information into you. Now, as I told you that how I represent information is very different from how your brain will represent the information. So what will happen is the only state that we'll have to come on the common ground. Common ground, basically what you will understand. Now what I'll make a representation here which you will understand. That's where language comes in. Okay, we speak a language so that this information that was in my brain, I somehow convert into a representation that you can understand. Now after this, there's one more step. This again goes to your brain in a very different fashion, and you store it in very different fashion. That's why sometimes people call human learning is very slow. So why is it slow? Because the bottleneck is this. This is the bottleneck. Yes. I'll come back to you. Okay, otherwise I'll lose this thought. So the bottleneck is this, because I have to put in information in a certain way so that your brain represents the information in its own way, and this representation is based on your experiences, inheritance, genomics. I don't know what many factors is this dependent on, because every human is different in that sort. Yes, I can take the question now. Now you see the two questions, important questions that I told you to ask yourself is, the first question is, okay, if there are missing values, what is the source of missing values? Okay, what is the source that they come from? And the second question I said is that you have to see why part. Okay, why should I handle missing values? So the discussion went into a different direction, and here they were told that it's not only that they make wrong prediction. Wrong prediction can be a consequence. It can happen because of that. And the point was that they learned the wrong distribution. And our job here as machine learning engineers would be to make these models generalize well. And how will they generalize? If your data represents the distribution, okay, the data distribution is learned very well. The data distribution is learned. Distribution, I have given a fair idea in the previous lectures. I assume that you know what distributions are, and we'll see that in mathematical notions and see rigorous definitions of what distributions are. So this is what machine learning basically want to do. They want to do generalization. That's at least what we want them to do, and they should not memorize. Okay, and now going to these missing values. If you now know the why part, so whenever you have the data, ask the question. Okay, are there, first is, are there some missing values? Yeah, there are. Okay, what might be the source of missing values? Because for your life, if you are thinking that you will be doing projects where you will have data cleaned, everything for you, because that's what people do in universities, colleges, they get data set and it's all cleaned. But when you actually solve a real world problem, you don't have data, collect data and do all these steps on your own. Okay, and because life is not so idealistic, which is being taught usually in colleges and schools. And but when you go to the real world and you find a problem there, you'll have to find data. Once you got the data is totally unclean, totally messed up, and then you have to pre-process that. And if you see missing value in these features, now you have to ask question source. Okay, find the source. Okay, can we do something about the source? Can you just remove this missingness next time if I get the data? Okay, if you found that, well and good. No, go to the next step. Okay, if there is no way of removing these missing values when you're in the real world, so what should you do? Now think, can I handle them? Okay, I can handle them. And why should I handle them? Because of this point. Okay, now today, so I'll just give a brief overview about what type of data do we encounter. Okay, give me a second so that you all know that these types of features can be there in the data. It will be just 5 minutes. Before ending today's session, I'll just introduce some types of data that you will have. So data in machine learning. This is very important to understand because most of the times I'm talking about data, and if I don't tell you, this will be a sin from my side. So what type of data do we encounter in machine learning? I cannot cover all the types, but most of the types I can tell you that you will encounter probably in the tenure when you will do this machine learning research or some sort of stuff like that. The first thing that you will have structured data. Structured data. So what is this? So while data will have structure, it will be organized data in some fixed schemes or in tabular form with rows and columns, like example was the data set that we had, or the banking transactions that we have, or let's suppose you have these school systems where you take data, or you have some other systems where you take these data, loan approvals and stuff like that. Okay, this is structured data. Then we have unstructured data. Unstructured. So what is this unstructured data? Well, there is not a particular structure. Let's suppose social media posts. Let's suppose product reviews. There you don't see a structure there. If you see medical X-rays, if you see any image, if you see audio, speech, music, so there is not a structure that you can define it in a table. Okay, this is that. Okay, this is a feature, this is that feature, and you can just structure it. So these are inherently they are unstructured data. Okay, if you want to do sentiment analysis, if you want to do object detection, if you want to do audio transcription, all of these will come under this unstructured data type. Okay, then we have semi-structured. So this is A, B, and C. Semi-structured. These are just names. I know, I think all of you will know that. I'll just cover it. So semi-structured basically means the data which is not strictly structured, but it has some structure. Let's suppose some JSON files be there, or emails. The best example is emails to easily explain. So email, all the emails, they have mail to, and they have, let's suppose, CC also, and they have the subject, and they have a main message. Okay, if you see, there is a structure, but if you internally go to elements, there is no structure in that because these just are there. Okay, this is sort of a semi-structured data. Okay, and then we have time series data. Time series data. So time series basically means why there's a temporal aspect. There is something that has to be done with time, like stock market. Okay, it runs with time. Let's suppose if you take data of your expenditure along the time. Okay, you are seeing how much expenditure am I making daily. If you have that data, your daily expenditure, that has a temporal aspect to it. If there is a temporal axis involved, okay, we call that data temporal data. So basically data points collected or recorded over the time, that, or maybe at regular intervals also. So that can be your time series data. Then we have something called as categorical data. Categorical data, easy to understand. If there are categories like male, female, binary values, even there can be more categories also. Let's suppose a category can be, take a simple example, what color is, if the color belongs to some 10 colors, so there will be 10 categories. So categorical data is that describes discrete values. Okay, some female is there if you have product categories, electronics, clothing, groceries and stuff like that. So these are categorical values. And then you have ordinal data. Ordinal data, I lost the track where we were. So this was, I'll go out of the letters, 1, 2, 3, 4, 5. So this is 5th and 6th. So ordinal data is somewhat like categorical, but they have inherent ranking to it. So there is a ranking. Let's suppose if you say customer reviews, if you see, so there you will see very satisfied, disappointed and something like this. These again are categorical variables, but they have an order in that. Okay, that's why they're called ordinal data. So there is certain order in that. So you can say, okay, the review, it was good, very good. Either you can have bad, very bad, bad, and then good, very good. Let's suppose these things they are from categories, but you can see the ordinal structure in that. Okay, and then again based on all of these things, you can have type of the features. You can have different types of features. Now, in the structure, in the unstructured, semi-structured, time series, or categorical data or ordinal data, what you can have is the features can be numeric. You can have numeric features. So in the numeric also, the features can be either discrete or continuous. Example is the discrete values can be, let's suppose if you have a date is again a discrete value. If you say you have a certain number, let's suppose you have age can be a discrete value. Age can though be continuous, but if you measure it in years only, okay, but discretize it, you have 0 year, 1 year, 2 years, something like this. Okay, continuous, let's suppose it's a reading from thermometer, something like that. Okay, this value is but both of these are numeric values. Okay, stock prices, they are continuous values. If you see number of clicks on advertisement, if you are having a website where you just see how many clicks were done on this advertisement or this post, so number of clicks a discrete value. Okay, so you can have these sort of features. Then you can again have categorical features, categorical data, and you can have categorical features like color can be this, or maybe a type of vehicle, bike, something like that. Okay, then text features. So you already know text features, they are to be made into the embeddings, which we call text embeddings. There are different techniques also, TF-IDF, word to vec, CBOWS, and a lot of these things. We'll study them one by one. And again, image features can be there. Okay, so there can be numeric features. Then what I said is there can be text features, and then there can be image features in the data. Or there can be, let's suppose now, audio features with this. So audio features can also be there, audio. And there can be temporal features where you have to deal with time. Okay, and there are different types of encoding also, how to encode time. And there can be what I call geospatial features. Geospatial features basically mean where there is a constant latitude, longitude, or there is something to do with space. It cannot be latitude, longitude also. There is something to do with the space. Okay, and let's suppose if you are making algorithm or route optimization, there should be some geospatial features. Okay, and then there are something called interaction based features. Okay, features that are combined by combined by two or multiple features. Okay, or derived features, engineering features are there. Okay, so all of these are some types of features, and this is some type of data, and this you should just keep in the head. When I'm speaking something, I'll assume at least you guys know this. If I say this is structured data, you know what this is. There is some inherent structure to it. If it's unstructured, no structure. If it is semi-structured, maybe some structure, but internally there is not overall structure. Time series data, there is a temporal component in it. Categorical data, it has a concept of categories in it. Ordinal data, again similar to categorical, but there is a certain hierarchy, certain order is there. Okay, and then features can be numeric can be discrete or continuous. Discrete is where you have a discrete number, continuous it will take a range of values. And then you have text features, image features, audio features, temporal features, geospatial features, and aggregate features. Okay, or engineered features they call, and a lot more maybe. Okay, but most these 90% of the things will fall under these types of features and types of data. Okay, so we have been studying about handling missing values. The important thing that we said about, I'll just revise for a couple of minutes so that everybody is on the same page. The first thing is I said find the source of randomness. Why is it important? Because sometimes you are in iterative method, you are training your machine learning or deep learning model, but you are on a continuous streak of collecting more data. So if there is some missing data and you now have an idea about what's the source of this missing, you can do something about it. Maybe in the next iteration you won't have that missing. So it is very important to find the source of this randomness. Okay, once you have the source of randomness, so I just told you what sort of randomness can be there. Let's suppose randomness can be if it is some survey. So randomness can be because of human error. If some human is there who is doing this data entry, okay, he or she might skip it, maybe mistakenly. It might happen, and sometimes some people might refuse to answer these surveys. Okay, refusal is there. Sometimes equipment error is there. By equipment I mean if you are making a data in which there are a lot of equipments involved, like let's suppose in the weather forecast you measure a lot of stuff, you measure humidity, precipitation. If you are working in medical domain, you measure blood pressure, heart rates and stuff like that. And so if there is an equipment error, so these things can also lead to the missing data, and there will be a lot more reasons than this. Okay, that you will find out when you work in that domain, and you will figure out those things. Okay, what is the source of this randomness? Rather than randomness, this is missingness. I have been calling it randomness. Okay, this is the source of missingness. And now after that, once you have that, I also answer the why part for you. Why do we care about this handling missing values? Because I said most of these machine learning and deep learning algorithm does not work well on the when we have missing data, because missing data somehow represents the incomplete information. Okay, these are the things that I told you. Then we said that statisticians, this is a tongue twister for me, statisticians, they have categorized these missing values into 3 categories. The first is MCAR, okay, missing completely at random, missing completely at random. So what does this mean? This means that when you have the data and you cannot find any obvious pattern from there, so the probability of getting a value missed is equal everywhere. So we call that missing completely at random. I told you there are 2 assumptions which people take. The first assumption is that there is no systematic difference in the observed variable between these variables and the missing data. That means the data with the missing values is similar to the data without missing values. So that is assumption 1. Assumption 1 is data with missing values is quite similar to the data without missing values. I'm writing too much. Okay, then the assumption 2 was that the relationship between missing value within that specific variable, it's again it is not dependent on that. So I said there can be 2 types of relations, if you can say, if this is the data, okay, and these were the variables. So we had feature 1, feature 2, feature 3 and feature 4. So let's suppose if this value is missing, the first thing what I said is this missing value does not have any relationship, or you cannot find any pattern with the other value that is there. Okay, so these things that are there. And the second assumption is that within this same feature it also does not have follow any pattern. So there is no pattern, it's completely, that's why it's called completely at random, missing completely at random. So these are 2 assumptions. Assumption 1 is it is unrelated, or it is not related with these other features. So I told you that difference also, that there can be different types of data. One is observed data, and then we have unobserved data. So I made a clear distinction between those. Unobserved data. So observed data, by that I meant, let's suppose when you are collecting some data, let's suppose you are solving a problem. So in that, what you will do is you will ask domain experts, okay, what features should we collect, because you cannot collect all the information, and that data which you will collect will be called as observed data. Okay, then there will be unobserved data also, which you have not collected. It might be important, might not be important. So let's suppose you are doing let's suppose doing some chest X-ray, and you want to find is the lungs of a person in a good position, or is there some disease or something like that. There can be multiple tests done. There can be lung X-rays done. There can be, let's suppose, sonography can be done. There can be heat maps can be formed. A lot of things can be done. But usually doctors resort to the easiest and the simplest option. They'll say, okay, get your X-ray done. So the data that you collected by the X-ray will be called as observed data, and the data that was not there will be called as unobserved data, because we believe that the data we observed, we can make some conclusions from this data. So here if you see these features, the features that we collected, features F1, F2, F3 and F4, all these features will be observed data, because we believe the task that we are going to do, the task that we are going to make a machine learning model learn is the task that, let's suppose, they have somehow these features get impacted by, these features impact that task. So we believe in that. So this is the assumption we make. Whatever features you collect, you think that these features somehow contribute to the thing that we want to observe, that we want to make conclusions about. Okay, and this is our observed data. Then there is unobserved data which we have not collected, as I gave the example in X-ray. So the first assumption is that there is no relation of these missing values with the observed data and within the same feature also. That's the second assumption. But if you see this missing at random now, so this is the first category, missing complete at random. Then we have missing at random. So what was this missing at random? So in missing at random, you can find the relation with the other features. Okay, these are the features. Let's suppose this is F1, F2, F3, F4, F5. I'll always make this data as matrix. So each of this will be called data point, which I am continuously reiterating, so that this gets into your long-term memory. So these are my features. Okay, or these are the features, or we call them independent variables,
and then we might have a class if it's a supervised learning setting. So this is a data matrix. So now in this MAR, which is called as missing at random, not completely at random, but this is missing at random. So in this you can somehow find a pattern. So in this the example would be, let's suppose completely random will be if you are having a weighing balance and you are weighing some patients over there, but sometimes suddenly something happened, this weighing balance got out of battery. So now for some patients the data won't be there. There is some equipment error for some random at some random time. So now the missing value at that point, that because it is not even governed, it has no relation with the other feature. So we'll call that thing as missing completely at random. So I also told you that mathematically it means that, so probability of getting any value of any feature missing is equal everywhere. Okay, somewhere, because it's totally random. So if you have defined randomness, so let's suppose if I have two variables, if I have defined randomness, how I define randomness. So if there are possibilities of 0 and 1, let's suppose, so we'll say the possibility of being 0 is equal to the possibility of being 1, then we will call it as random. Similarly, so here that's why I'm saying possibility of this feature being missing is equal to the possibility of this feature being missing. So I'm saying the probability of one feature being missing will be equal to the probability of other feature being missing. This is missing completely at random. But when you have this missing at random, so in this what will happen is, so you'll somehow find a correlation. So you'll somehow find a correlation like this. So when you, let's suppose, ask incomes to the rich people, they somehow do not, sometimes they do not report their incomes. Okay, so now you can figure out that thing. Okay, this person, let's suppose, if it is rich, he or she is not reporting the income. So we'll call this as missing at random. So one example is that in healthier study, younger participants are less likely to let's suppose report some of these things. Let's suppose some things can be heart rate and things like, because they consider themselves as healthy. So again, if a man and woman, let's suppose in a study of satisfaction, younger employees again are less likely to answer some questions because they might feel that company might fire us or something like that. So when you see a pattern like this, when you see that there is observed data, can somehow explain the missingness. So observed data, this can explain why the data is missing. So you can somehow see the pattern. So because now you have seen the observed data. So let's suppose you had this age, you had the age column, and then corresponding to age, you had the income. You said, okay, the elder people are not reporting their incomes. So this is highly likely that elder people are not reporting their incomes. Sometimes randomness can be like this. If yesterday, which I said, so if you have a gender, sex, male, female, and then they have to report their age. So you will see that females are quite reluctant to tell their age. So now based on this observed data, whatever we observed, so you can find some correlation of this. You can find some correlation of missingness with these observed data. So then we have missing not at random. So this was when you have the relation with the unobserved data, because you have not observed that. Okay, let's suppose the example that usually people give is when you have say you are taking a survey forms. Okay, you are taking a survey form, let's suppose in healthcare, and some patient just went away and he did not want to again give the more information. Maybe something happened to him. Now you have that incomplete information, and that missing value is basically dependent on unobserved, the data that we did not see. Okay, these were the different types of random, and they are well mathematically defined, but I don't want to get into the mathematical details of this. So I just wanted to cover these three things: so missing completely at random, missing at random, and missing not at random. Okay, why did I tell you this? Because sometimes you have to make assumptions. Okay, which type of missingness is in my data, and based on that you have to take decisions and accordingly do either the imputation or you have to do the deletion accordingly. Okay, now how to find this? As I said yesterday also, it is nearly impossible to find it. Nearly impossible to find which type of missingness is it. But the only thing you can do is make an assumption and accordingly take decisions of how to handle that missingness in the data. I think we have a question. Yes, go ahead. So now one thing over here is, so these things are easy to handle. If you see this and this, these are easy to handle. But if you have this, where the assumption is that missing data is based on the unobserved data, so it is quite hard to handle. Okay, here you can drop the value and we'll see different types of these how to handle these missing values. So this you can handle, this you can handle, and this is quite hard to handle. I think we have ended the question. Yes, go ahead. It's a good question, very good question, very relevant question. The question asked was, when we collect data, so we take some features and let's suppose down the line we figured out that some other features are also important, should we collect them also? So this is also a reason of missingness. So what happens, let's suppose you have a problem, you are trying to solve the problem. So while defining the problem, you thought I should collect this data, I should collect, let's suppose, feature 1, feature 2 and feature 3. So after a while you said, okay, now I have collected this data, now I feel if we collect this also, you hypothesize this, okay, if I collect this feature also, somehow my algorithm or whatever I have will perform better. Now after, let's suppose this happened within some time t1 frame. So now in time t2 frame you said I'll collect f1, f2, f3 and additionally I'll collect f4 and f5. Now again this can be a cause of missing values, this can be a source of missingness. But the question was, how do we basically do that? We do not just say, okay, we are taking these features, we are done with this. No, sometimes we change these features, we keep on doing this, but because you never know what features can be important. As I said, in terms of, let's suppose you are a doctor right now, because being a doctor or being at least a researcher, so you sometimes believe that only these things do impact this, but sometimes you find a factor which was not considered even, and which was not even discovered at that point of time, okay, and then that factor will be also included. So you have to always ask the question, are there some more factors? So that's why it's better to ask domain experts. Yesterday also I sort of touched this point. So whenever you are defining a problem, so for the first thing is you'll get domain expert. Okay, is this problem feasible even? So you might have even seen a meme, the dream of artists is a nightmare for an engineer. Okay, an artist can make anything on a paper, but is it feasible in the actual world? It becomes a question. The same thing over here. So when you define a problem, now you made this problem so generic, then you go to domain expert and ask them, okay, can we somehow collect this data and can we solve this? Okay, I'll take a little digression to this. So actually I wanted to make a recommendation system for studies. This was a personal pursuit, a recommendation system for education. This is what I wanted to make, because what I felt is the recommendation system that we have, they're called as collaborate based recommendation systems. This was my problem statement. So I said the recommendation systems that we have, let's suppose in Netflix and YouTube, they are based on what is called as collaborative filtering. So what is this? So this has an assumption. The assumption there is that the similar users will have similar affinity towards products or items, whatever you call them, or the reverse is also true. The similar items, if they will be loved by the similar users. So that was the assumption based on that. If you see YouTube, let's say, so if you like a video, or maybe let's suppose you spend a lot of time on that video, so YouTube will somehow start recommending the similar videos like that, okay, which are closer to that, based on what, maybe let's suppose you have a user 1 and user 2, and these two users are quite similar. So whatever this user saw, so they'll recommend user 2 the same thing also, okay, because there is a high probability that, because user 1 and user 2 are quite similar and the similarity is calculated, and then they'll recommend this also. And similar for this, let's suppose if you saw item 1 and if there is some other item 2 which is quite similar, let's suppose Fahad is the user here. So item 1, Fahad was quite interested in this interest is seen by measuring how much time you spent and where you interact in that duration of time when you're watching the video. So now item 2, if it is somewhat similar to item 1, so they'll again recommend you this. So this is how the recommendation system in general works for these YouTube, Netflix, and maybe for shopping, Flipkart, Amazon and these shopping websites. But for education the problem was like this. So I said, let's suppose if somebody is watching a video on education, if they are watching, let's say, deep learning, if they are watching deep learning video, now the thing is, what should I recommend the video? So based on this I can see, the question was, is the user understanding the thing? Okay, this was a question that I had to ask myself, is the user understanding? And for this understanding I had to make a lot of metrics. I have to come up with metrics and maybe make user interact in the middle of this. The first I have to see, is the user interested also? If the user was not understanding, so my best guess would be user lacks the prerequisites. The prerequisites are not there. So what should I do is, I should somehow, before this deep learning, maybe let's suppose I recommend mathematics videos. Okay, it is not based on similarity now. Now I have to change the recommendation system. I have to say, okay, you watch this video based on the metrics that I collected, and I have to share probably the prerequisites, because somehow I came up with these metrics where the metric says me you don't understand the video properly, but you have the interest because you spend the time over there. Okay, and I have to give the prerequisites. And if I felt that by using this metric of understanding, I felt that user understands these videos and maybe he is somewhat an advanced user, should I now recommend the follow-up video or maybe a little bit advanced video? Okay, this was the problem statement. Okay, the first question that I had to ask myself, I have to solve is, okay, what metric should I collect so that I can reach the conclusion that this I have from this metric I can say the user is understanding. Okay, I have to collect features. Okay, and this is where I actually wanted you to steer. So the thing is, here the first thing was this understanding. What features should I capture so that I can conclude from these features that the user is understanding, and user is understanding the topic, or user is not understanding. What score should I, how should I quantify it? This was the question. Okay, so here I have to do a lot of things. Asked people, okay, what do you call understanding? Okay, why do you feel that you understand? Or they can say, okay, you have to see facial expressions. We talked to psychologists and they were saying, okay, you should track facial movements. I said it will become complex algorithm if we and then we have to take consent and things like that. Then we have to like settle for some other metrics. Okay, give some videos and see the reaction time. And again, this metrics, we never came up with the idealistic metric for the understanding purposes. Okay, and that was the question Fahad asked. Okay, when you have a problem statement and then you have to collect these features, and now you never have clarity about what features to collect. If the problem is so new, and if you ask the domain expert and sometimes you feel it is computationally either infeasible or there is not much knowledge, but down the line you feel, oh, something was discovered today. Okay, we can also do this. Okay, can we somehow include this? Let's suppose tomorrow this facial recognition, somehow we came up with some new technique by which the facial recognition, it became very easy and somehow anonymous, so we can include that feature also. So this is a continuous process. Okay, the more data you collect, the better your algorithm gets, and the data that you did not collect, it's not that it's not important. Okay, now you make a best guess, or maybe you put your bet on these features. Okay, I know about this, I have this much limited knowledge, and based on that I have an assumption that whatever problem I'm solving, these features will impact that. But it is not a complete, that's why the more data you feed to it, the better it gets, and we'll see that in probability. I hope I answered the question. Yes. Now you saw the types of randomness. Now coming back to this, you saw the types of missingness. Now we'll have to see how to deal with this missingness, how to handle this missingness. The first method that we saw was called is called as complete case analysis or list-wise deletions. I hate the names though. Okay, so in this, the easy thing is you drop these things. You drop either the rows, by rows I mean data points, or you drop the columns. Okay, by columns I mean features. So when do you drop these data points? So what you do basically is you see, okay, if this data point contains a missing value, let's drop that data point. Okay, in features, if you feel that yesterday the question was asked, if there is, let's suppose, 50 or 60% of this missing value for a feature, should we drop that? So the answer to that was, it completely depends on the domain that you are working in. Say you are working in a domain and you should assign the weight to the features also. There should be a weight assigned. Okay, this feature is this important. So if there is a huge amount of missing value in that feature, so it is better not to drop it because this feature has a lot of weight. Let's say, okay, let's say feature 1, if this is very important feature, if it has 70% of data is missing from this feature, so still it's but this feature is carries a lot of weight in making the prediction, what a task we are solving. So it is better not to drop it. But sometimes you feel that you have hundreds and thousands of features, so one feature doesn't make sense if it has, let's suppose, 90% or say 70% of data is missing from the feature, and if you have thousands of features and you somehow feel that this feature I can drop, so you have to make these you have to make these design choices. Okay, should I drop this, should I not drop this, and should I handle these missing values? So all of these are choices, and you have to talk to domain experts, and you have to talk to yourself also if you are solving the problem and you have a good understanding of that problem at that point of time. So you have to accordingly think, should I drop this feature? Because if you drop the feature, it basically means you are losing some information, not at the data point level but at the feature, at the problem statement level. So data loss can be of two types. So one loss is basically you have the information you have all the information, but you just drop some points, so that's one information loss. Other information loss is that the problem statement level, where you thought these features, let's suppose features F3, F4, F5, they will contribute towards the problem because they somehow can help me to solve the problem, and you have to make a decision, should I drop these because now I am getting a lot of missing values in certain features. Okay, and again in both the cases you are getting you are deleting the things and you are having the loss of data. But I thought I'm pretty sure that you have the clarity of what is the meaning of losing the data at row level and what is the meaning of losing the data at column level. Okay, and now we'll see in the data set that I actually introduced in the previous session. I'll just bring up the code and I'll show you that. So here is this code that I also showed you in the yesterday's session. I'll just go through it. So this is our data set that we have. I have just downloaded this data set from Kaggle, diabetes missing data. So I read it because it was a CSV file. I just read it and I printed the data frames head. If you can see, there are pregnant, glucose, diastolic blood pressure, skin fold, serum insulin, BMI, diabetes pedigree, and age class. So just to again define you these features are actually, when you have this thing, the first thing that should come in the mind is you should research about all of these features. Okay, what is the meaning of this pregnant, what is the meaning of this glucose, because by no means we'll be experts in every field. So you'll have to either research on your own if you are solving it for a project, and if it is actually a thing that will go in the deployment and millions of people will use it, so it is better to talk to domain experts to just remove that possibility of error or possibility of being doubtful. So here if you see, the pregnant basically means how many times did the person got pregnant. It applies to males. This glucose level are the glucose levels, and diastolic BP is pretty clear. Skin folds, this is a skin fold of triceps, if I remember it correctly. So and it is measured in millimeters, and this is thickness. So this is serum insulin, and all these features have their own things, but the only thing that you have to see is the patient diabetic or is the patient not diabetic. That this is the class. So this is actually a classification task. So this is our data set. So now in order to see the missing value, so what I said, the first task is when you have any data, so first you should do the exploration. You should see, are there missing values? If there are missing values, what of these features have missing values, and if you can see the distribution and how severe is the missingness in different features. So what we can do is we can do it in this pandas. So if you say df is null, this will return you sort of a boolean mask. So it will say true for the values where there is a missing value and false for the values where there is no missing value, and then you sum them up for all the columns, and when you print it you will get something like this. Okay, when I ran it, so you saw pregnant, it has no missing value, glucose 5 missing values, diastolic BP 35, skin fold 227, 347, and something like this. And then you again have a function of this info. You have a function info which prints the summary of the data frame. So here if I just print this, so you can clearly see over here, it showed me that there are 768 entries. Basically the size of the data set is 768. There are 768 data points. Okay, now what you have is, it shows not null count. Okay, and it also shows the D type. So if you see, not null count is 768. Out of 768, all the 768 are not null. That means null value is 0. So this is of int64, and accordingly you can read the other values also. Now you can see the percentage also. So if you want to see the percentage, you just have to divide it by the length of df, that is 768, and then multiply by 100 to find the percentage. So it'll tell you the percentage of missing values. So here if you see this, percentage of missing values is just 29%, 48%. Now if you want to make a plot out of this, okay, so how can you make a plot is like this. Because you have done a lot of matplotlib, so you just have this missing count, because that's what we calculated above in the above cell, and then you just plot it, missing count dot plot, and what is the kind of that? It's a bar plot, and figure size is this, color is this, and then I'm just doing some labeling over here. So this you can see it which video over here. Then you can also see the correlation between missing values. So what's the meaning of correlation? Does one feature affect other? Let's suppose if age is missing, is something else also missing? Is there a correlation in the missing values? If one of the feature has missing value, does it guarantee that other will also have missing value? Is there a certain correlation? So you can do that by using correlations, covariance matrix, and things like that. We'll see in detail when we'll reach probability and statistics. So here you can see this correlation. It can be shown by heat maps. So you can see this, there is this correlation. The more brighter it gets, the more correlation these things have. This correlation is between the missingness of the features. If one feature has missing value, and if it is a correlation with other, there is a high possibility. If it is a positive correlation, there is a high possibility that other will also have the missing value. Now again, if I want to see the proportion of missing values, here there I show the bar chart. Here I'll show this pie chart. If you see this, missing percentage is this much, and now if I want to make this bar plot, and this is how to make this pie chart over here. Okay, so the task, why was I doing this? Why am I showing you this? Because whenever you have this, whenever you want to basically explore this, the first thing you should see is how can I visualize these things, how can I see this in the visual format, because sometimes visual things are appealing and it maybe unveils a lot of patterns. So it's better whenever you see missingness, ask these questions. Don't directly go, I'll handle the missingness. It is better to explore these things. Any questions over here? The question asked was heat map and correlations. I'll just make this code window disappear. Heat maps and correlation. We'll take this topic in detail. I'll just probably explain you in some minutes. So what correlation basically means, if let's suppose you have a feature 1 and you have feature 2. If this value gets increased, let's say I'll take this is a numerical value, and if this value also, you can see an increase in this value. So you see somehow these things are correlated with each other. That's why I'll make a graph like this, and you see this is feature f1 and this is feature f2, and if you draw points and you saw something like this, the value of when this f1 is increasing, at the same time f2 is also increasing. So when you see this, you call this positive correlation. Okay, because somehow you can say something about the other thing when you can see it. And correlation is not causation, by the way. Causation means what causes other things. Correlation, sometimes you can see a clear thing in correlations. What you can say is sometimes a country which eats a lot of chocolates, their age, the lifespan of the individuals there is quite high. But you can say there is a correlation, but there is no causation. It doesn't mean that eating chocolate increases your lifespan. Okay, but there is a correlation seen. If you eat a lot of chocolates, and you can see the countries which consume a lot of chocolates, they have the lifespan over there is more. Okay, but this does not make it a cause. Okay, you should eat more chocolates. Okay, people sometimes use this correlation causation in a very subtle way, and they confuse people. And let's suppose if people are let's say have certain characteristics, and they might have correlation with some other thing, but it's not necessary it will be causation. So if you see this correlation, I mean if I increase this, if f1 has increased value, accordingly f2 gets some increased value. So this is called as positive correlation. Then you can also see negative correlation like this. So when one value is increased, other gets decreased. Okay, I'm just saying it in hand wave arguments, and there are mathematical notions to this also. Okay, so this is what I mean by correlation. So knowing something about one thing can tell you something about the other feature. Knowing something about f1 can tell you something about f2. So this is what I mean by correlation. So again, to highlight this point, do not get correlation confused with causation. Causation is something else. Okay, so this is the correlation. Now heat maps are a way to visualize them. So if you see this heat map that I showed you here, let me just go back there and show you that heat map. So if you see this heat map, okay, so this bright color basically means there is perfect correlation. 1 basically means there's a perfect correlation. So this diagonal is 1. So why is it 1? Because you know that this is glucose over here, and that is glucose at the x-axis also. So feature with itself has 100% correlation. If you see glucose over here and glucose, that's what diagonally you see 100% correlation, or I'll say value of 1. If you see negative values, there is a negative correlation. Okay, but these values are quite close to 0. But if you see there is some good value over here, the higher this value is, there is more positive correlation. The negative it gets, there is negative correlation. 0 basically means it almost looks there is no correlation at all. That's what this heat map means over here. Okay, that's why we have this is called as color bar. I think we have covered this in matplotlib pandas. This is color bar. So starting from 0, let's suppose, and it goes to let's suppose 1. So the darker it gets, the better correlation it has. Okay, is that clear now? It is actually a very nice question also. So I said you should not conclude everything based on these numbers. So here it shows that this serum insulin and this skin fold, they have a strong correlation. So right now we can say, oh, if they are very much correlated. But what I said is, when you look further in the data, you will feel that this serum insulin and skin fold, they have a very high number of missing values. So that's why the correlation shows that there is a lot of correlation. But sometimes it cannot be the case also. So that's why you have to look into this. Okay, you cannot make the statements just based on correlation. I saw a correlation, that means it. But I'll just show you that. So if you see this, I think we have made a graph over here. You can see this skin fold and serum insulin, they have a lot of missing values. That's why you can see correlation. So what do we want to see over here is, why is it negative for BMI versus others? That you have to look in the data set. Can I see negative values over here? Yeah, it is. So BMI has 0.01 with glucose. that there will be it's almost near to zero. There is a little bit correlation, but almost near to zero basically means there is no relation at all. If you see this, this is glucose and diastole B, it also has negative correlation, but this is not actually correlation. But if you see the values are quite weak, 0.02. Okay, if it was a higher value, we could have seen it in the data. But I was answering this question. So if you see these sort of correlations, you should be asking the questions. Okay, is it actually there are a lot of missing values, or is there actually some sort of pattern over there? So that's why you must explore this missingness. It's not just okay, I saw these many missing values and then okay, let's go ahead handle the missing values. So it is better to explore these missing values, see if there are correlations, see if some values are more missing, see if there is you can do something about that. That should be the first step. That's why I'm emphasizing more on it. Okay. Many of the people miss this out. They directly start, okay, I have a missing value, let's handle them. Okay, the thing that I want you people to do is, whenever you have data, be Sherlock Holmes, see the data. So if there are missing values, because we have to do a lot of steps in data, because the only rule that I want you to remember is garbage in, garbage out. The better data you have, the better model you will have, irrespective of how complex or how simple your model is. Because if your data is very good, if your data is somehow representative of your distribution, then you will make your model learn better. Okay, so if you see the code for these transformers, it's not pretty long, it's not pretty difficult also, but the difficult part is over the data. The better data you get, the better quality of data you get, and the better engineering hacks you will make, and the better model you will create. Okay, when you have this, the first thing you should do is you should explore the missing values, because that's what is done in the real world. You don't directly go and fill the missing values, do this and that. Yes, we have a question. Yes, Muzaffar. The question asked was, if we give the model the clean data, so but in real world we won't get the clean data, and then if that data is given to the model will be of no use. So what we basically do is, whatever cleaning you do on the data, so you do the same cleaning when you test it. Okay, let's suppose you have this data on training time, and you cleaned it, and you got it into a certain format, and then you trained the model onto this. So what I'm saying is, when you get a query from the real world, so you do almost the same steps, because you have to clean this query steps also. Irrespective, data coming is garbage, so you will make it really presentable before giving it to the model, because that's what the model was trained on. Okay, is that all right? So sometimes what happens is, if you clean data too much, अगर data को बहुत ज़्यादा clean किया जाए, what will happen is, at the testing time, or at the inference time, I should say, at the inference time when you deploy this model. So if your latency is quite high, sometimes that model is also not good. So I felt with one of the projects. So we cleaned data so much and we got very good results, but that model actually was not deployable at all, because it was a real-time application and the latency expected was quite low. But due to this cleaning, because we were getting a query, and query has to be, that data had to be cleaned. So that's why you also again have to take a trade-off between this, how much to clean the data. So is this a real-time application, or is the application where I can take some time? It's all right. So data cleaning also, because as I said, you also have to clean the test time data or inference time data also. So you again have to make decisions accordingly. I am cleaning this much, I am taking these steps. That's why I always say document these things. You have to document what cleaning you did. Okay, because at the inference time you have to see that, because model is trained on a certain things. Okay, if you give model only that thing, it will perform better. If you give it something else, it will speak out gibberish, because the world it knows is the cleaned version that you gave it. So you have to clean the data at the inference time also, but you have to make a trade-off. Okay, how much to clean? If I clean it way too much and the model is perform better, but I have to because this cleaning now takes a lot of time. So now you have to make decisions accordingly. Okay. This is actually a good question. I got a chance to say this, because when you will deploy these things, you have to do these things again. Any other questions? The question becomes, let's suppose I took this is my one data point, and if I have to transform it to get a better representation, and on this representation the model performs better. Now the question is, if it takes a lot of time, let's suppose in our case it took 4 seconds, and now we have to relook all the things that we did. Can we somehow drop the complex? Let's suppose some of these things, when we were doing representation, it was an order and square algorithm. Let's suppose sometimes it might be order say n log n. Can we somehow drop this? Can we make it linear? Can we do some other engineering hack so that we can drop this computational time, and we'll get the same representation maybe within 0.1 second or something like that. Okay, and you have to make these decisions. So, but it is better in the exploration phase. If you can make a better representation, maybe then there is a room for improvement. You can say, okay, if I got this representation, my model is performing better. That means this representation is good. Now the question becomes how to drop this time, how to get this better, how to clean basically. So this is again cleaning. So if you see, this is again preparing or cleaning data. So this is preparation of data. Now the decision has to be made. Okay, how much time should be given? And it depends on the application also. It was very good question that you asked. Any other questions? So whatever I showed, this is not end of this thing. So you can use a lot of graphs that you studied. You can use a lot of other things to analyze the missingness. To analyze, okay, what is the kind of missingness? Okay, what structure is there, and what things are there? You can ask a lot of questions. I'm just giving you breadcrumbs because my point here is to make you think. Okay, now the first thing that I showed you, complete case study. We'll do that also. Now we'll drop these things, and then we'll see what is the change in distribution. Okay, we'll see this listwise deletion on the data set. Let me just delete this. So how to delete that? You have to just say drop NA. Okay, I'll just copy this code and I'll again show you the code window and go back there. Okay, now what I will do is I'll listwise drop it. I told you deletion can be of two types. You can delete the rows and you can delete the columns, data points, or the features. So here what I did is I said df listwise deletion. So do this deletion. Okay, now once I delete this, so what should I check is, so I should check a lot of things. So once I delete this, what are the changes in the distribution, how distribution got changed, and what are the different statistics, let's suppose mean, mode, variance, how they got changed, and we should also have a look at these. Let's suppose here I just dropped it. If I just say df.head now, okay, so this, if you see, now you can see these are the values are there. You cannot see any not a number value. If I say dot is null, so hopefully I should get no value dot sum also. If you see this, everything was clean now because that is not null, because what I did is I just dropped these values. I said drop NA. That means drop all these data points where you see even a single feature which has missing value. Just drop them. Okay, now you have to make a choice when to drop it. If your data set is usually large, so then we will drop it. Let's suppose if not a number, these null values are less than 5%, less than 6-7%, so you will say, okay, I don't care about the 7% data. So because now at least I think my data, other data that has not missing values is representative of the distribution, is representative of the population. So I can remove this data easily. So you have to make these things also. Now what I'll show you different I'll show you all the plots for all the things that happened before we drop these values and after we drop them. So how to do that? We have column list. Okay, I'll show you for one column first. Let's suppose we write columns. So the code that's written over here is probably a little bit bigger, so it is better to write the code on my own. Oops, give me a sec. So what I'll do is I'll just take one column. So I'll show you distribution of column wise. So this is my column. Let's say I'll take column 1. Let's say pregnant. We have a column pregnant. Pregnant had actually no missing values. I think glucose had certain missing values. Skin fold had missing values. So let me just copy the skin fold and then see the distribution before and after. This again is to show you what things to check. Okay, so oops, so these are all the columns. I just want to take skin fold. I'm copying because I want exact spelling. This is again getting copied as the whole. It's better to write skin. I think fold is this, right? So now we'll have to plot this. So I'll say plt dot figure. So I will have a size of, let's say, 10 cross say 6, something like this. Now what I'll do is I'll plot this. I'll say I'll also have to import cbon. Cbon is there. Cbon.kde. KDE is that KDE plot, because I have explained this KDE plot when I was explaining CDF and PDF. Now df of column. So this is column. Okay. So take this column and make this and give the label. Let's say is before. Df is the original data frame. So before, oops, label is equal to before deletion. This is before deletion, and I should also give color. Color is blue with small caps, and then I should say shade. Give shade also is true, and then line width also. Line width is 2. Let's see if it plt.show. I have to see this if it. Oh my god. So it is showing int is not this. So let me just do one thing. That's why I don't usually write the code, because we have to debug it a lot. I think this line should work, and this is column. Okay, so let's see this again, showing the same value. This must be an iterable. So I have to again draw one more plot. Let's do this. Let's just paste this and just delete this whole thing, just have one column. Okay, you can see this. Okay, so it's better to just paste it and have only one column. So you can see the distribution. This before deletion, the distribution of the data, this is for the pregnant, and after deletion you can see these things got changed. Why did it got changed? Because there were values which were, there were data points which were dropped. You can see there is a shift in the distribution. So green distribution is the initial distribution, and then we have after deletion this yellow distribution. So again we can change this. We can say glucose. Okay, this is that distribution. You can see the shift in distribution. So if I again take all the values I want to show you all at once. That's how I wrote it when I was writing it. So this is these are the change in distribution. Okay, this is pregnant, and this is how distribution got changed. Glucose distribution got changed a bit. So for this diacetol BP, not much effect. Second fold, not much effect. And you can see serum insulin almost similar. Okay, and it might be hidden here. So you have to take decision, okay, how much distribution is getting changed when I am dropping these things. Now again you will have to see if the distribution getting changed, or what are the factors. What are the static variables. Let's suppose you have say mean, median, mode. How are these things getting changed? Okay, just give me a second. How are they getting changed? You also have in pandas, you have those. Okay, and how many rows are getting deleted. So I have written a code line over here. If you see, pretty easy. So you see rows before, this is the rows shape, and when you drop these things and then you take a shape of this, and I want to see how many rows were deleted. You can see rows before deletion is 768, rows after deletion this much, and these many rows were removed. It's a huge chunk of data that was removed. And you also have to see this here. It is pretty easy to see, but when the data gets bigger and bigger, and you will have to think, okay, should I drop it or not? Okay, and I have also plotted some pairwise plots, but I don't want to show this because this is pretty big on screen. Okay, you can also see variance and other these statistics measures. So let's say I'll paste a line of code over here. You see, let's suppose this is my deletion and the stats, because I have this describe function which tells me the stats. So stats for variance, stats for this mean, 50 and standard deviation, all of these things before and after. If you see this is the comparison of mean, how mean got changed for pregnant, glucose, diacetolic, and all these things should be seen. Okay, this code is pretty much easily understandable, because we have done enough coding now. Oops. Give me a second. With all these things have to be checked. Okay, so if you see the change before, mean before was 3.8, mean 50% was this much. This is all before, and if you see after is here, so 3.8 got shifted to 3.3. There is a sudden, there is a shift, actually a huge shift. So if you see, this is actually 122 and 121, not much shift. Okay, that you can see what in these graphical ways also, and you have to take decisions according. Okay, should I use this or not, because the distribution gets shifted too much, and if it is not getting shifted too much, can I use this? Okay, it is okay to use, because now I feel the distribution is the same that we had. So I'll tell you an actual case study that we had to deal with recently, where we were dropping this. This is not only about dropping, so it has implications in other realms also. I'll tell you that. So what actually happened in our case? Oops. In our case, we had data, and the data was of humongous scale. So we had data was of 1.6 lakh data points were there. Okay, and in each data point we had 9 regions. It actually was an image like this. It was an image, and in each image at average 9 regions were selected. Okay, so this made it 1.4 million records around that. So this data was quite huge, and now we had to train our model. So now we're thinking, okay, if we have a huge compute power, it will easily require some 120 gigabytes of GPU memory, and that too, let's say, within the single GPU. But now we had to somehow pick the data from here, so we only used 10% of the data, okay, from this. So 10% of the data was somewhere around, I think, 200k samples. This is what we used. But now, while sampling this, while having this is actual like deletion. We're doing deletion of these data points. Now the thing that we have to keep in mind is distribution should be somewhat similar. Okay, so by distribution what I meant is, so in that, let's suppose we had reports. In reports we had certain terms. So we said, let's suppose we had terms A, B, C, D, E and F. So in actual 1.4 million records, we saw how many A terms were there, how many B, C, these terms were in those reports. So that's, and we saw distribution. We made a distribution like this. And if you see your WhatsApp group, I have shown you there. Okay, so this distribution was given. So when we took 200k records out of this, that's around 10% of the data. When we took this much data from this, the distribution was to be kept similar. Okay, we had to truncate the data in such a way so that we don't disturb the distribution. Okay, that is exactly the case when you do this listwise deletion, or you do this complete case analysis. So you have to care about distribution, you have to care about mean values if these are numerical values, you have to care about all these statistical values, because you don't want to change the distribution. You don't want to change, because your data is representation of your population. Your data represents your population, represents the population. So if you somehow do the deletion, so if it did not become the representative of the population, then you are in real trouble. Okay, it becomes problematic. So usually I say the case study when the Nokia people, everybody among us have heard about Nokia phones. They trained their machine learning model on European people, so they were detecting faces. Now you see that it was not representative of the population, because you have people of different ethnicities with different skin color, with different face cuts and things like that, and it was not detecting African people. It was saying them not human. And it was just categorized human, not human. So it was for the African people, it was saying not human, because it was not trained on that. So when you are deleting the data, you should make sure that you still represent the population, because again, keep that thing in the mind that you have to generalize. Machine learning algorithms should generalize. They should not just memorize the thing. So you have to generalize. That's the reason you have to show them all kinds of data. Okay? When you delete the data, you should keep this in the mind. So whatever subset of data you have now, so that should be representative of the population. It applies to when you are sampling, it also applies to when you are doing the deletion. So you should do all of these things over here. Okay, make sense to all of you? Okay, my job is not to make you just learn these things and blindly you will just apply these things everywhere. So my job here is I am just doing something. There's a principle based on which I am doing these things. So I was plotting these distribution plots. I was just measuring these statistical measures like mean, variance, and standard deviation, or things like that. So this was just to showcase you what things should we care about, because we have an end goal and there is a way to reach end goal. There is not only one way. There can be multiple ways, and you can sometimes come up with better methods also. Okay, so it is better to keep your brain open, not just follow everything that I say and you just do that much. Otherwise it will restrict you as a thinker, it will restrict you as a student. So the better thing is just understand the principle that I am making. The principle is that whenever let's suppose you do this listwise deletion, this is the principle. We are looking at this. So it means whatever plots you have to use, you use them. Whatever things that you have to use them. It is not that you will be restricted by only this, but you will see most of the people will, let's suppose 90% of the time they'll use these things which I am saying now, but sometimes you will solve a peculiar problem which will be totally a problem which is unsolved, which was never solved. That time these graphs won't help, but the thinking will still help you. The thinking that I want to inculcate is, okay, the principle is this, you should work on principles rather than just mugging up the things. The principle was we have to handle missing value, and if I delete the things, this is the things that I have to check, and there are a lot more things that we can check, and there are things because I don't know all the problem in all the domains, so you will sometimes work in some other domain. So it is better to just have this thinking, maybe practice this thinking on some other data set, and not to just memorize, okay, we have to check distribution, we have to check mean, variance, this and that, and we're done, and then we'll apply this. And people sometimes they teach in this style. They'll show you, okay, these things are to be done, as if it is some sort of procedure, some sort of algorithm. You have this problem, you do this, done, and then apply this. It's a very wrong way and very weird way of thinking. So what happens is, basically you are trying to say that one hat fits all. It's not the case like that, because you will be machine learning scientists or engineers, while you will be solving problems of different domains. So from me you should get the thinking. Okay, you should say, okay, our sir is not trying to push, you should memorize this. Rather, he's trying to, okay, the way of thinking. There is a goal, define the principle for you, and then see what things can you do and what things can be done in order to reach that. Okay, and sometimes you have to adapt new thinking. You have to adapt new techniques, new strategies to reach that, and which even people won't be using. So it is better to have think these things in that direction, not to just mug up these things. And that's why you always keep on questioning these things, and you keep on questioning when you are doing it, keep on questioning when I am teaching it. Okay, let's move ahead. Now we'll see what are the disadvantages and advantages of this technique, just for the sake of completion. Advantage. What are the advantages? First thing, it's very simple, ease of implementation. So now pandas, scikit-learn, all of these, they just give you one method and you just apply that and you drop it. Okay, and it preserves the original data somehow, integrity of original data, because the first thing is ease, the second thing is integrity, because you don't introduce anything new, so the data is still in the thing that it was. So that's what is called the integrity. And then we have this consistency. Okay, so when this ensures that the same data was used. So let's say now the same data subset was used, because you do not do anything to it. Okay, and we made no assumptions at all. We said we made no assumption of missing this, we just drop these values. But what are disadvantages? So now you saw the disadvantage, you lose the data. Disadvantage, again I am just mentioning few, just to show you that you also have to think in those lines. When you do something, think about, okay, what are the advantages? Oh, easy implement is good, integrity, consent, this and this, that, there. Okay, what other things are good in this? What are the advantages? And should I use this because it has a lot more advantage? In my particular scenario, it makes sense to have these advantages. And are the disadvantages, like let's suppose I say loss of data. Loss of data is a disadvantage because you lose a lot of data. Okay, and then there is a bias it creates. It creates some bias because let's suppose you deleted something and it shifted your distribution. Okay, and all these things. And then you cannot use it on, let's suppose, temporal data. Why can't you use it on temporal data? Because you'll be then removing those time. Let's suppose something is time dependent, you are collecting data on every day. If there are missing values, you just remove these values and somehow you will mess up with this temporal axis. So there are a lot of disadvantages also. I'm just mentioning few, and it depends on domain. Okay, here I just meant loss of data, this is universal. Temporal just applies for time. But again, the thinking process that you should have here is, okay, when I'm using this technique, what are the advantages? So if there are these advantages, does it make sense for my particular domain? Okay, does it make sense for my particular problem? It has this disadvantages. Are these disadvantages very lethal to my domain, or very lethal to my problem thing that I am solving right now? And you should take decisions accordingly. Is that clear? Any questions on this? Now from here onwards, I'll just randomly speak out a name and I'll tell you to help me out. Okay, now what we'll do is, now we have to handle missing values. The easiest way was to delete it. Okay, now we have to get to more sophisticated methods because we don't want to lose the data. So now we'll do what is called as data imputations. Whenever we find missing values, we'll have to do imputations. Okay, and we'll go through that. Okay, so can you tell me what things can we do? Let's suppose you have data. Now you have data like this. This is feature 1, feature 2, feature 3, feature 4. Let's suppose we'll restrict our discussion to numerical data. Numerical data. I'll call out a name and then he'll help me out. Let's suppose we have 2, 4 missing value and 5, 6, something like this. Some missing values over here. Asif, can you tell me what comes to your mind? How can we impute these values? By imputation, I mean what values can be substituted here? What thing can be done here? And keep all the discussion that we did so far in mind. Don't change the distribution. Try to at least preserve the distribution. Try to preserve the statistical variables like variance, mean, and stuff like that. So what comes to your mind directly? What are the things that can be replaced over here? Because now the question is, I don't want to lose data. I cannot just remove this row or column. Asif, are you here?
Yes, we can use mean for that.
So we can use mean. Can we do something else?
Let's mean.
You can use median also.
Yes,
okay. Or we can use mode. So again, I'll tell you the principle. The principle here is replace these values with the central value, with the central tendency values. Okay, this mean, median, and mode, all of them represent something central. Okay, let's suppose we have data. and in the data we want to see what is the central tendency. So what are the other points approaching towards, and what is, if I take a point at random, so what is the point that I'll get likely. Let's suppose I'll take it like this. So we have 2, 4, 8, 1, 2, something like this. So what I mean by this mean, mode, and median, so all of these somehow represent some central tendencies. So if I just take the mean of these values, let's suppose I have these values 2, 4, 1, 8 and 2. This is 10, 11, 15, 17. So 17 divided by 5. Okay, and let's make it 18. Let's make it 18 by having this 2 also. So this is 18 by 5. Or should we make it 20? 18 by 5 is this is, and this is my mean value, let's say. Okay, this is my mean value. So this mean value tells me that this is the central tendency. By that I mean, so all the other points will be around this. So somehow this is the central tendency, or will be centered around this, somehow like this. Okay, that's why I want to replace it with the mean, and this is one of the techniques that we do. So we call it mean. This is called as univariate imputation. Okay, so univariate imputation. So what is the meaning of univariate imputation? That means you just take one variable. Okay, in order to impute value, in order to replace that missing value with something, you just take a one variable. That's why univariate. You just take one variable, and based on that you replace it. You replace these. So what are the techniques in there? The first thing that we saw is mean. Then we have median, and then we have mode. And what else can be done? We can also have some arbitrary value. We can also have some random value. All these things will be considered in univariate analysis or univariate imputation. So we'll replace it with mean of that column, or median of that column, mode of that column, and some arbitrary value or some random value, and we will have discussion on each of these things. Okay, so what do you think are the advantages of this mean imputation? Asif, what do you think? I've given you the answer, I think, before I spoke it.
And if we replace it with by median, the overall the distribution will not change.
So the simple answer would be, because now this is central tendency. If I just have this, because our other data points will have the same tendency, so that we don't want to skew it. So usually by mean I will not skew these other statistical measures. So it is better to just have it mean. But mean had its own disadvantages. If there are a lot of outliers, and then there will be a problem. But still, we'll see all of these. Okay, this is what is in the univariate imputation. We'll see it one by one. Okay, and we have the data set with us, and we'll see it. So let's start with all of these three together, and then we'll take the arbitrary value separately, because arbitrary value and random value will take it separately. So mean, median, and mode. Okay, it can be they can be done in pandas also. They can be done in scikit-learn. I'll write sklearn. This can be done in both of these. So we'll see both the approach, because sometimes you'll use pandas, sometimes you use sklearn, because sometimes in deployment people use sklearn. So it is better because at testing time or at inference time you will be having sklearn there. So it is better to do it with this. And sometimes it also becomes, because if you are doing the exploration, you are doing it with pandas, then you train the model. Okay, but better approach would be to use sklearn, because usually at the time of deployment, that's what you will be using at the inference time also. Okay, let's go to the code window and show you it there. Okay, I'll show you both the approaches. Not difficult, you can just find this code everywhere on the internet. Okay, once we just clear this. Okay, so now what we should do is, there is a simple function fill NA. Okay, fill NA is the function that you will use in pandas. So I'll just paste this code. Okay, so this should get copied. So if you see this, so now we have df with missing. So this is the actual df that we had, data with missing values. I just made a copy out of it, and then I'm imputing it with mean. So how to impute that? I'm saying fill NA df mean with missing mean. So this function, or dot mean, what will it do is, it will calculate mean for all the features. So wherever it sees this not a number value or missing value, it will fill this with mean. So this is the mean value, and the same thing happens with median and the mode. Okay, and what is the mode? Mode is basically most frequent, and mean and median are defined for the numeric things, and also this mode is also defined for numeric things. But this mode makes more sense when you have categorical data. Okay, you see the most frequent occurring thing. Now what I'm saying is, I'll just remove this arbitrary thing. Okay, I'm removing this arbitrary because we'll take it separately. So now if you see, So this is what will happen to this. So now we had original this, and just we removed this, and it'll have 0 0. So once we have this, now we want to make all the same comparison that we have. So this is how we do it in pandas. So we just have to use this fill NA. But if you are using scikit-learn, okay, in scikit-learn we have a class over there which is called a simple imputer. Okay, I'll show you that also. So from sklearn you will do it like this. So from sklearn.impute, and you will take this simple imputer. So now you will make an object out of this, and you will see the strategy. What strategy are you going to use? Just let me copy this. So simple imputer, you will make a oops. My mouse is somewhat laggy. So you see this, I just made an object out of this simple imputer, and I named it mun impute, because there is an argument strategy over here. You can just go on the documentation of scikit-learn, and maybe we'll take a separate lecture on scikit-learn. But here I just wanted to show you, this is the class, and we made an object of that class, and I give an argument strategy is mean. Okay, and then I'll apply this for the data frame. I'll just apply it fit.transform. Oops. If you see this, what I said is, I said mean imputer, the object that I formed, dot fit dot transform df with missing values. Df with missing values is the original df, and then I said columns are this df missing values dot columns. Apply this strategy on this, and then I'm calling it df mean impute with sklearn. Okay, I'll do with the same for medians and mode. So I'll just copy and paste it here, because now you have understood how to use this. Oops. Why is it not happening? You now see this. So the first thing is you have to import this class, and then you make an object out of this, and then you have to give strategy based on the strategy that we'll be using. Mean, median, or most frequent. Basically means the mode, and you will see it after this. So I'm just printing the head. Okay, this is what I'm printing. Now I showed you both the ways, by pandas way and the scikit-learn way, and probably in the assignments you'll have to implement everything from scratch. You would probably use any library. Now we'll have to see how the variance got changed, and for all these things. So let's say we'll take this. So df. So now I took this feature glucose, and I said df with missing is the feature, and this is df with mean imputed, mode, and this, and I am seeing how did it got changed. So if you see the distribution, there are 4 plots. If you see, this is original, blue one is the original, and this is orange one is the mean imputed, and this is the median imputed, and this is the mode imputed. The red one is the mode imputed. If you see all of these, somehow the distribution did not get shifted much. So you can see the distribution somehow remained the same. So you can just change this value, and what are the things that we have? I just wanted to print call. Let's suppose we have diabetes over here, and I can also see that. Okay, you can see this. You can see all of them almost overlapping. Okay, if I just remove these, you can see, okay, almost all the distribution remain the same for this diabetes. So I have other variables. Let's suppose age. If I just paste age over here, you can see the distribution almost remained the same. Okay, that's why you have, first you will check these, and after that you will also check, let's suppose, are there some other things, are there some other outliers introduced, and for that you will plot Box-Cox plot, which we have seen. You can also see mean, median, and mode, how are they changed overall. Okay, and all that code we have seen earlier also. I'll just paste it over here. I have just commented a lot of code. If you see this, I'll just remove this part of the code. Just printing these things, so you can see this is comparison of status before and after imputation. So you see before, this is mean, this is 50%, this standard deviation variance, and now you can see it over here also. So mean did not get shifted too much. You can see the data somehow remains similar. So you can also also plot these Box-Cox plot to see what happened to outliers. You can also see correlation, was the correlation changed, and things like that. You can see a lot of these things. I am just showing you some of the plots, and rest you can do it on your own when you are sitting and when you are seeing these videos. And at that time, what you will do is you will just check, let's suppose I'll also check for, let's suppose, correlation between these things. The initial correlation was this, what is the correlation after I did the imputation. So all of these things have to be checked, and not just this, and much more, whatever you feel for the particular data. Now again, advantage and disadvantages, it's simplicity of use. So you can just let me just hide this window now. Hide the code window, and you can, again, the same thing is, this is very easy to use. All of these things are very easy to use, but a little bit complex, because you have to go through all the data and then compute the mean, median, mode. Okay, and it becomes like order n algorithm for at least all the features. You have to do this, but what it does is it also preserves the data. My hands are quite shaky because it's too cold here. And then you can see that, let's suppose in some cases it doesn't introduce bias, and you can have consistency across all the variables. Wherever you have this NaN, you can see, okay, I replace them with the same number. Disadvantages, it sometimes distorts distribution. In this particular case it did not, but sometimes it does that, it distorts distribution, and this is very problematic if it does this. Okay, and it again sometimes introduces some correlation or removes some correlation. So it what I can say, distorts correlation also. Let's suppose if there was a correlation, now you introduce some of these values on your own, it can distort these correlation. Again, it can introduce bias also. Okay, and when you have complex data set, it cannot be good, because there will be multivariate relationships, so it's not that good. So as it can also introduce correlations and stuff like that, and there will be a lot more than this. Okay, these are the disadvantages, and these are the advantages. I don't want to cover them, but I just want to give you breadcrumbs, so that whenever you are using something, you will think about in this direction. Okay, what the advantage that it provides in this particular case, and what the disadvantage that will give. Okay, usually mean value, it's suitable for the like numeric data, where you will see that my data is almost normally distributed. By normally I mean some sort this distribution is there. Okay, mode imputation is used when you have categorical data, because there you don't have the concept of mean and median, so there you use mode. Okay, so even because sometimes what happens, if there are a lot of outliers, so mean is affected. So if let's suppose we have this 2 1 4 6 2 something like this, if you just have value 100, okay, this 100 is an outlier. Now if you see, the mean will get shifted, so mean is affected by outliers, but median is not affected by outliers. Let's suppose if you compute mean of this, okay, let's suppose this value was 1 actually, but somehow somebody introduced the 0 0 and it was a typing mistake. Now this is an outlier in here. If you now calculate the mean will get shifted. So this is 2 1 and this is 3 7 7 and 6 is 13 14 15. So this is 115 divided by how many? These are 6. So this is the mean. The original should have been, let's suppose this is 15 and 16 by 6. So you see how much difference there is. So just by introducing one outlier of 100, you saw the mean got shifted. Now the median does not have this problem. So median is not affected by the outliers. So what is median? You just sort these values and pick up the middle value out of that. Okay, so that's why sometimes median is used instead of mode, because mean gets affected by the outliers and median does not get affected by the outliers. And if you see a small data missing, so it is better to use these. You see, okay, so there are only few values missing, so if I just impute it with mean, median or mode, so it is better. But if you see complex data set, don't use it. Okay, and you will make all these conclusions by yourself. I am not just putting these thoughts. Okay, I'm not making these rules. If you have small data set, just use this. So you have to come to these conclusions by yourself. You will draw a lot of graphs, you will do a lot of analysis, and then you will probably even fit these things. You will use model with this, you will use model with some other imputation techniques and see why does it perform better. Okay, when it performs better, you will say, okay, this imputation technique is way better, and you also will have to answer this question of interpretability. Why is it perform better? If I did this imputation, why is it perform better? Is it represent the information better? Is it represent the distribution in a better manner? So all of these questions you have to answer. It's not like, okay, I am just throwing the arrows and it is performing better, so this is good. So it is not that way. So whenever you do certain imputations, the question you should ask yourself, why is it doing so? You'll have to interpret it. Okay, so that it gives you more details about the test. It gives you more details about the domain. Okay, is that clear? Because this is very important. Some people miss it. So they say, okay, I'll use at random all the techniques, and that's why some people use grid search. I have seen people using grid search for which imputation technique is better. They'll just pick up the grid search, and whichever this imputation technique gives the better results on test and train data set, they'll say, okay, this is better imputation technique. But this is not the case. The important thing that you people should do is interpretation. Okay, I imputed this with this, and now I got this as results. Now you should answer the questions for yourself. Okay, I imputed with mean, median or mode, and it gave this much higher accuracy, and why is it better now? And you should ask these questions and make it interpretable. Otherwise you will be, as I said, shooting arrows in the air, and you don't know why is it perform better. And then on top of that, if the neural networks are not interpretable, you are introducing more non-interpretability. So it is better to answer these questions on your own. Okay, then comes our arbitrary imputation. Any questions on this mean, median, mode? I'll again record this. So the important question asked was, so if we, let's suppose, take some imputation mean, median or mode, and we saw that on certain thing it's giving better accuracy, can we just conclude that I'll use this? So the answer to that is it will lose the interpretability. It will lose this aspect. So the question is in the machine learning is, when you're doing something, you will have to ask the questions. If I introduce this, if I impute the value by this thing, if I impute these missing values by median, mode or mean, so if it gave better results, next thing you should ask yourself is why did it happen? Okay, because it will reveal a lot of information. Sometimes you will most of the times it will happen that you will say, okay, it did not change the distribution much, it's learning it. But sometimes what will happen is, when you impute it by somebody, you might make the distribution simpler to learn, and you might even change the distribution, and you will feel that this distribution was very easy to learn from machine learning algorithm, it is giving better results. But in the real world, that is not the distribution that you wanted your algorithm to learn. So this is very important to ask this question to yourself. So here I said I am sort of against using the grid search for the complex projects. For the simpler, I'm okay. But if you are actually making an algorithm or making a machine learning model or deep learning model where the lives of people depend on you, okay, so please don't use these automatic techniques where it will lose interpretability. Okay, you should ask yourself the question, if it is giving the better results on this particular imputation, why is it so? Okay, and then at least come with some explanation, okay, and then test your hypothesis. Whatever hypothesis you made, okay, this is happening because of this. Now I'll make a case against it. I'll make a case in favor of this. Okay, and if, while testing the hypothesis, if it was wrong, then you'll have to come with the rational. But do not just remove the possibility. I will not ask questions at all. That should not be done. Okay, I'll just show you one more plot, and then I'll again take questions. So one more plot that I have here is, if you want to see outliers, have you introduced outliers, things like that. Okay, just show. Let me show you the code window, and here it is. So the code for that is over here, because I know that you will stop these videos and you will write this code on your own. So I just took this glucose, this diagnostic diastolic BP and BMI, and I have this DF imputed mean, median and mode, and I am seeing these box plots for it. Box plots basically tells me the outlier and interquartile range and all these things. We have covered those things in detail. So you see almost nothing got changed in this data set. So you see that this box plot is similar. This is original box plot. This is mean, median and mode. Original, mean, median and mode. But you can see, you know that box plot is usually used to detect outliers, to see how interquartile range got changed, and then what was the mean value over there. So you can see all of these details in this box plot over here. Okay, so this, please, when you're watching these, do pause it and write each of the code line on your own. I think we had a question. Yes, Muzaffar, ask. Now the topic that we'll be switching to is imputing with arbitrary values. Okay, so arbitrary value imputation, it again involves the filling of these missing values with some user specified constant. Okay, user will specify constant, and there is a rationale behind. There should be a rationale behind that. Many other people will tell you can fill it with any constant, but there should be rationale. So what is the rationale? Because let's suppose you are a domain expert. Let's suppose in medical case you are a domain expert. So you know, let's suppose glucose level of 100 is reasonable. You will say, okay, impute this glucose level, wherever it is missing, you impute it with 100. So you have, because you have a plausible explanation to that, because you are a domain expert. Again, say let's suppose diastolic BP in this case, replace it with some, let's suppose, standard blood pressure, something like that. So these are arbitrary values, but these arbitrary values have something to do with the domain, or have something to do with a plausibility. You can explain it, why are you using this, okay, and if this gives the better results, and you can explain, okay, this gives better results because of this condition, okay, and that's why it's arbitrary. Why is it arbitrary? Because each of these features will have a value that makes sense to impute them, and that we call them arbitrary values. Okay, otherwise we would have said it some fixed value, but it's not fixed at all, because we have infinite features in infinite problems. So in each of these features we'll have some value which makes sense according to that domain. So that's why we call it arbitrary value. But as I said, this arbitrary value, when you choose them, it should have some rationality behind that. I'm using this specific value because of this. I believe from the domain because this is, let's suppose, as I explained in let's suppose glucose. So glucose level of 100 is a plausible domain specific value. Again, the diastolic pressure of 80 is a standard blood pressure, that's a baseline. Again, the BMI, replace it with the average, let's suppose healthy average BMI, something like that. And all these things may come from the domain. I just give the example of the data set that we have, but if you have some other data set, you must talk to domain experts or do some research to find the arbitrary values which make sense to use. Okay, this is how the arbitrary value should be used. Again, to focus, you should not miss out on the interpretability part, because you are getting a better accuracy, and why part should be clear. Why are you getting the better accuracy? So how to do this? Again, you can do it in pandas by just saying fill NA, then the constant value, and you can say in place or out of place, howsoever you want to do it. Let me just go to the code window and show you this. So if you have, this is the imputations that we said that we did earlier. I'll just go to this cell. So if you see that this is my arbitrary data pandas where it has these missing values, and then I'm saying replace the glucose value with 100, replace the diastolic BP with 80, and replace the BMI with 25, and these are the standard values, and these values have the rationale behind that which I explained to you. And sometimes many of the people, if you learn, they'll say arbitrary means drop any value, but that value should actually have some rationale behind it. Now if you see this, so here it does that, and now again you have to do the same comparison. You have to do how the distribution got shifted, and let's suppose what was the change in variance, what was the change in we have also in scikit-learn we can do this. I think we have a scikit-learn code here. Yes, we have scikit-learn, that by scikit-learn we can also do this. I just wanted to show you before moving ahead how to do the comparison. So if you this again simple imputer, so I made a dictionary out of this where I said glucose 100, diastolic BP is 80, and BMI 25. Now what we do is we go the column wise, and if the value is in these items, so what we do is we say simple imputer strategy is now constant. Okay, and fill value, what should be the value, and value will be taken from this values. Okay, this dictionary I am reading, iterating through it, and I am saying use the strategy as constant and fill the value by the value that is what there. That's why I have made a dictionary out of this. Okay, and this is the way scikit-learn does it. Okay, you can do it with pandas and you can do it with scikit-learn, but scikit-learn has an additional thing. You have to just make a class out of it first. Okay, that's what we have used. Or you can directly use simple imputer like this, or you just make a class with the strategy of this and fill the value with the constant. And then what you will do is you will again do the comparison. You will make a lot of charts, and you will make see how did the variance change before and after. Let me show you this. I actually had to code it, but it just is getting repeated. You can see it like this. So I'm saying this is my original stats before, stats of variance, and then I'm saying mean, 50, all of these things before and after. df arbitrary is not defined. Let us just delete these things. This is for sklearn. sklearn will do the same things. Okay, you can see comparison before, and I also made charts. This is the same code that we used previously. I just changed these things now. Okay, so this is before and this is the after, and these are the change in these mean values, change in this comparison 50% between arbitrary and before standard. This is standard deviation, this is variance. You can see all of these things, and you can also see outliers, how distribution got changed, and all of that stuff. Okay, one more technique is end of distribution. I think we'll take it tomorrow because we have a couple of more univariate imputations. One is end of distribution, then we have random imputations. I think two are there, and then we'll move on. The same thing will be done at categorical variables also. I'll tell you what are the different things that we can do on categorical. Whatever we saw so far was for the numerical variables, numerical features rather. So after that we'll move to the categorical data. In the next session we'll take the end of distribution and these random variable imputations, and then we'll also deal with the categorical missing values, and then we'll move on to the multivariate imputations where we'll see prediction based imputations, like we'll use KNN for prediction, we'll use some algorithm which is called as mice for the prediction, and some other predictive algorithms for prediction of these things. Okay, and I'll stop recording over here. If you have any questions, please feel free to ask.